post our cultural space.
Okay.
If probably you can post it.
Yeah, well, you already had it also.
Yeah, I don't have a word.
Someday you will. You may have to like accept
Yeah.
it and record it.
As you're Italian there.
Sorry?
So you're that from English.
It's an Italian. Why are you going me? Why are you such Italian? Nice in Germany.
Yeah. Hi. So it's with or without mask?
I think it's whichever you prefer. For better or for worse, he's unfortunately had it within the last 90 days. So it's not a big risk. I think.
No, okay, I can keep it on. Don't worry.
Well, what do you think? Should I announce it? Okay. Well, I'm going to come over and stand with you just to briefly hello. We're very pleased to have Jona Lelmi here today. Jona is a third-year PhD in Bonn, working under the supervision of Tim Lowe, working on things in PE, cognitive variations, and especially theoretical data science. And today he's going to be speaking on and also right now he's visiting UCLA. He's been at UCLA since February, staying till July, working with several people there, including Gail and Kim. And so today, Jona is going to be speaking about the large data limit of the MBO scheme for data clustering. So thank you again.
Okay, thank you very much, Kate. And thank you for the invitation here in Santa Barbara. I mean, it's very nice to see all California. So you should always take the opportunity to see every place you are invited to. So as Katie was saying, my PhD advisor is Tim Laux, and we are what I will present now is a joint work with actually two joint works with him, and they are about the large data limit of the MBO scheme for data clustering. And I will say in a moment, since there were already questions about an MBO scheme, I will explain in a moment everything in this title. So just to start from the very beginning, so in data science, usually you have a data set, a very large data set, and you would like to identify clusters in this data set, points which are usually similar to each other. And similar, usually it means in a Euclidean sense. So you would like to identify points which are close to each other in a Euclidean sense. And there are various ways of performing data clustering, and variety for doing these are those who are graph-based. And the idea of graph-based learning is that you are given a data set. So these are just vectors in some large space RD. And on top of these data points, you construct a graph, a weighted graph, where the vertex set V is given by the data points, and the adjacency matrix W is the weight matrix in a certain sense. And you impose that the diagonal of this matrix is made of zeros, so you don't want the graph to have self loops. And for points xi and xj, which are different from each other, you put a weight between the node I and node j, which is a function of the Euclidean distance of the data points. And usually this Euclidean distance will be either a Gaussian, or you could think of either being the characteristic function of an interval, 0 epsilon. So in that case, you have that you have an edge if the distance is less than epsilon, and you don't have an edge otherwise. Okay, so these are all possible choices of functions. And okay, then you can define the degree of the node I, which is the sum of from j with j from 1 to n of wij divided by n. And you can finally define a very useful object for data clustering, which is the graph Laplacian. In this case, we take the random walk version. This is just a matrix, which is given by minus this 1 over n d minus 1 w, where w is the weighted matrix, and the d, as you see here, is the diagonal matrix of the degrees. And in this talk, the goal is to study an algorithm, the MBO scheme, which I will talk about in a second. And the goal will be to cluster a data set into two clusters. So actually, what we'll talk about could be done also for an arbitrary number of clusters, but to keep it simple, the goal will be to find a function chi, which splits the data set into two subsets, C1 and C0. And yeah, here on the right, you have, for example, a construction of a data graph with choosing eta, as I said, the characteristic function of an interval 0 epsilon, where you connect the data points if the distance less than epsilon, and you don't connect them otherwise. But it's just a picture, it's not really important. Okay, so we will be interested in studying the behavior of an algorithm in the large data limit. And what do I mean by the large data limit? So usually in practice, when you want to cluster a real data set, you are given a data set with where the points have a lot of features. So they live in actually in a large space RT, but practically most of a lot of the features will be correlated to each other. So actually the true dimensionality of the data set will be much lower. So that's why usually in theoretical data science, you assume that the data points lie on a k-dimensional Riemannian submanifold of your space. So we will be assuming that M is a k-dimensional Riemannian submanifold. We will assume that on this manifold, we are given a probability distribution, absolutely continuous with respect to the volume form, according to which some data points are distributed. So I will assume that xi are IID random points on the manifold distributed according to this probability nu. And then the idea is that given these assumptions, you can construct a sequence of graphs, Gn, where the vertex set is given by the first n data points, and the weights are defined exactly as before, just that now you also rescale by a parameter epsilon greater than 0, which will be going to 0 and then goes to infinity, because essentially you want the weight to localize more and more as epsilon goes to 0. You want to concentrate. Yes. Yeah, exactly. So I call it random graph because the points are random. Okay. Okay, the Laplacian now is rescaled by factor epsilon squared, so that in the limit you get actually a continuum operator. I mean, this is a very famous result by Kaufman and Lafont that says that if you rescale the Laplacian in this way and you take a sequence epsilon n converging to 0 with a given rate, then you have a consistency result that says that whenever f is a smooth function on the manifold, the Laplacian on the nth graph applied to f converges up to a constant to this weighted Laplacian here. This weighted Laplacian is defined as minus 1 over rho squared divergence rho squared grad f. So it's the weighted Laplacian with respect to the measure rho squared volume form. And it's with a minus sign just for convention, so that this becomes a positive operator. And this constant here is a constant which depends on the choice of the function eta, which you define with which you define the weights. But for the rest of the talk, it will be 1. I mean, it's not important. Okay, so this is the setting of the large data limit. So now I want to talk about really the algorithm that we want to study. So this is the MBO scheme. And MBO stands for Merriman, Benz, and Osher, who introduced this scheme for the approximation of the evolution by mean curvature flow, actually. And then it was actually modified, or at least rediscovered by Bertozzi and co-authors to perform data clustering. So you have your data set V, and the goal is to, as we said before, is to find a characteristic function on this data set. In input, you give a first guess for the clustering that could be obtained with another clustering algorithm, maybe much simpler than the MBO scheme. You give yourself a step size greater than 0, and you give also yourself the number of iterations that you want to run. And then the output, of course, will be a clustering. And the algorithm is very simple. You just iteratively produce a new cluster doing the following steps. The first step is a diffusion. So you have a cluster which becomes from the previous step, so KL, and you apply a matrix. So here delta is the graph Laplacian. So this exponential is just the exponential of a matrix, so it's a matrix, and you're applying a matrix to okay, this is can be identified with a vector, of course, because it's just a function defined on n data points. And so you obtain another function here. And the second step is thresholding. So you update the new cluster as the set of points where this diffusion here is greater or equal than 1/2. So this is the algorithm. Very simple. And for example, let us see what happens on this toy model on the 2 moons data set, where the goal is to construct an algorithm which is able to cluster, to identify correctly these 2 moons. The initial guess is obtained by a linear algorithm, actually, which is k-means. And you see that we perform 1 iteration, 2 iterations, 3 iterations, and essentially you get very good clustering here. Okay, so it works very well. And yeah, I want to spend a few words also about the corresponding scheme in the continuum. So in the
So here we use the like theta diffusion, the equidirective act on this three infinity scale, right? So what connection with the diffusion act? Like
yeah, no, here. So actually, the point is that this U is actually really the solution to the heat equation on the graph associated to this graph Laplacian here. Because if you let this h vary and you differentiate with respect to h, you get exactly that this function solves the heat equation on the graph with initial value given by this chi L. Yeah.
What's the criteria for this algorithm to work? It works for every data or works with data with some features?
What do you mean?
I mean, so this one works really well. It's going to have more. It's going to have very complicated.
Yeah, I mean, it works. Of course, it will be maybe less accurate, but it works very well with a lot of different scenarios.
Yeah. I mean, there are very different scenarios that we set. Is there a mathematical property or physical property, or what features does this scenario have?
I mean,
Just trying to.
yeah, essentially. I mean, of course, I mean, when you with all the toy models in the toy data sets, it works. I mean, with MNIST, with the
example, many algorithms work.
Sorry.
Many algorithms work for this example.
Yeah.
It's not the only one.
Yeah, of course. This is just it was just to have a picture, but I mean there are results about the benchmark of this algorithm which are very, very good. But in this talk we don't concentrate on the benchmark. We want to understand. We want to concentrate on what's the problem, what's the theoretical justification about this algorithm. But I mean for the benchmark there are a lot of results by Bertozzi and co-authors where they compare these also to clustering algorithms based on the first on the sign of the first eigenvalue of the Laplacian. They compare it to a very different algorithms and they get good results. But of course they always use these for example the MNIST data set, these toy models with the 2 moons, because these are the somehow the data sets with which you try to compare to other things. I mean, yeah. I mean,
interesting question to define. It seems like it's a very open area to define appropriate hypotheses on your data set so you can get quick clustering guarantees.
If I remember correctly, a few years ago, someone put that to the construction problem which one works and which one doesn't. Hard to maybe understand from the
I mean, in practice, I think I would always try a bunch of them and see what works best. But this is there is no guarantee that it will work, because I mean most of when you then apply things, most of the times it's really knowing well also the problem that you want to solve. Then you understand which may work. But I mean, yeah, for practical application, it's there is no guarantee that it will work. Yeah. No, here, so here H is fixed, so you solve this integration at this time, and then you look at, this is not a function, right? and you look just at the set of points on the graph where this function is greater or equal than 1. Okay. Okay. So it's yeah. Other questions? Okay, then yeah, as I said, this scheme actually came out first to approximate evolution by mean curvature flow in the continuum, and here the idea is that you start with a smooth domain. So here chi is a characteristic function now on the manifold of a domain with a smooth boundary, and you want to use this algorithm to approximate the evolution of the boundary of omega by mean curvature flow for the times h, 2h, 3h, 4h, and so on. And to do that, you just do the same thing as before. So you inductively define your approximation by defining u. Now, I mean, we are in the infinite dimensional setting. So now u is really defined as the solution of the heat equation at time h with initial value given by the previous approximation. And the heat equation is taken with respect to this weighted Laplacian. And then the thresholding step is obtained by defining the new approximation as the set of points where this function here is greater or equal than 1/2. So you see there is a complete analogy. So just that on the graph we are in the finite dimensional setting. Okay. And okay, and one can show actually that these algorithms really approximate the evolution by mean curvature flow. So, but there is what is really interesting is that I mean, mathematically speaking, is that there is a minimizing movement interpretation for this scheme. So both for the MBO scheme for data clustering and for the MBO scheme in the continuum, when you pass from chi-L to chi-L plus 1, so when you do one step, you, instead of doing this diffusion and thresholding, you could actually recover the new approximation by solving a variational problem, which is this one. So if you have chi-L, which is a characteristic function on the graph, to obtain chi-L plus 1, you can minimize this energy here, which is defined here. So here, this is the thresholding energy on the graph, and it's nothing but the inner product of 1 minus u and the diffusion of u at time h. And then there is also a dissipation term, which is similar to the term defined by the energy. And the same result holds true at the level of the continuum. So when you want to approximate, when you want to find chi-L plus 1 given chi-L on the manifold, the same is true, just that now the thresholding energy is defined instead of a scalar product, it's defined with an integral, okay? It's an integral with respect to this measure here of 1 minus u and the diffusion of u at time h. Okay, so there is a complete analogy. And why this minimizing movement it's important? So it raises three questions actually. And the first one is raised by Bertozzi, and it asks whether there is a consistency of a single step of MBO from the discrete to continuum in the following sense. So let's assume that you have a smooth domain on the manifold, and you take the intersection of this domain with the nth graph, okay? Then you perform one step of MBO on the graph, and you want to understand whether this one step of MBO on the graph is a good approximation for doing one step of MBO on the manifold. In other words, if I do one step of MBO on the graph, do I converge to the solution of one step of MBO on the manifold? This is the first question. Then more intrinsically, the fact that the MBO scheme is obtained by this variational problem says that if I perform enough iterations, I will be close to a minimizer of the thresholding energy. Okay, so it's interesting to understand what happens to these minimizers as the number of data points goes to infinity. So what's the asymptotic behavior of the minimizers? And third question, which is related to the second one, is to understand which local minimizers will be picked, it's important to understand the trajectory that is followed by this gradient descent. So it's interesting to understand what happens to the dynamics of this scheme as the number of data points goes to infinity. So now we will focus on answering partially, let's say, to the first two questions, and then if I have time, I will also talk a little bit about the third one. So remember that we are working in the large data limit setting. So we have a lot of points. We have a sequence of IID points on the manifold, and we have constructed a sequence of graphs associated to the first n points. And so for each n, I can define the thresholding energy on the nth graph in the following way. So this is just the inner product on the nth graph of 1 minus u and the diffusion of u at time h. So here the energy depends on three parameters: the number of data points, the localization parameter that I use to define the weights, and the step size that I choose in the algorithm. And then we have the following first result, discrete to non-local result, that says the following. So if you pick epsilon n, which converges to 0, with a given rate, so this rate is the same that we had in the result by Goldman and Lafont. So for every fixed h greater than 0, you have that whenever you take a sequence of functions, each on a different graph, converging to a function u on the manifold, and I will explain in a moment what, in which sense we have this convergence here. Then you have convergence, at the level of the energy. So the different energies evaluated at these different points converge to the thresholding energy of the limit point. And this holds whenever h is fixed greater than 0. And this result is actually a corollary of this second theorem that we have, that says that under the same assumptions, whenever I have a sequence of functions defined on a different graph, which converge to a limit point u on the manifold in a weak TL2 sense, and I will explain in a moment what it means, then the heat operators actually converts the weak convergence to a strong TL2 convergence. This is the same analogy that we have on Rn. On Rn, if you have, let's say, initial datum which converge weakly in L2, now classical L2 space, then the heat operator will force the convergence to be strong in L2. And okay, let me say what is this TL2 convergence, and then I'll come back to these results in a moment. So the TL2 convergence was introduced by Garcia, Trillos, and Sletcher. So the point is that we have a sequence of functions defined just on finitely many points. And I would like to compare these functions here to a limit function which is on the manifold. And of course, one way would be I restrict the function on the manifold to those data points, but this is not possible because in general, the limit will be just a measurable function. So the idea is to use optimal transport to compare these functions. So we have this probability distribution on the manifold. We have our IID random points distributed according to nu, and I define for each n the empirical distribution associated to the first n data points. Then I say that un converge weakly or strongly in TL2, provided there are transport maps that transport nu to the empirical distribution nu n, such that satisfy two things. The first requirement essentially is that nu n should converge to nu in the Wasserstein sense. And the second requirement is that now un composed with the transport map converge weakly or strongly in L2 on the manifold. Okay, so this is I mean, a very simple notion of convergence, but you have to come up with this idea. And yeah, and now coming back to these results, why do I say that the first theorem is a corollary of the second one? Well, because look at this energy. This energy, here we have an inner product. If I assume that un converge an inner product of something which is converging weakly times something, the second theorem is converging strongly. And this is in complete analysis of the classical L2 space. Weak times strong convergence is passes to the limit. Okay, so this is why the first theorem is a result of the second one. And actually, in the same way, you could pass to the limit also in this dissipation term. So actually, this first result already gives a positive answer to the question raised by Bertozzi, because we are saying actually that this whole energy, let's say here, so the energy plus the dissipation term, converts gamma converts to the corresponding thing in the continuum. So this gamma convergence already implies the convergence of the minimizers, or in other words, the convergence of one step of MBO. And for the second question, already this gives partial answers because this convergence here is actually a bit more than gamma convergent. Here we are asserting that every convergence sequence is a recovery sequence. So we already have the convergence of these the local minimizers of this energy to the local minimizers of this energy. We are not completely satisfied by this because here we are still fixing a parameter h greater than 0. We would like to study actually the joint gamma limit obtained by sending also h to 0 jointly with n to infinity, but this is seems to be a hard question. So we concentrated first to sending n to infinity, taking h fixed, and then we take h to 0, which is yeah.
Does this Morgan process depend on the magnitude of M, or in other words, they have a perfect magnitude?
No. This is independent of the dimension. The dimension enters here only here. I mean, the dimension of the manifold. You mean? No, n is the dimension. N is going to infinity because it's the number of data points.
M.
M. Sorry. Yes. It's the dimension of the manifold only enters here in the rate at which epsilon n converges to 0. But otherwise, it's independent of it.
Can you remind us how epsilon n was defined?
Epsilon n is the localization parameter that you use to define the here. Yeah, you take a sequence, so you take a different epsilon for each n, and you assume that this is converging to 0 with that rate. And yeah, and then so we said, okay, the joint limit is difficult, so we take first n to infinity, and then we take h to 0, and h to 0 is the following result. But it was not known before. And probably this is the most difficult part of the paper. So we identify the gamma limit with respect to the classical L1 space of the thresholding energy on the manifold. And the gamma limit is given by this energy function right here. So it's defined on the set of functions u, which are 0, 1 valued. But so if u is the characteristic function of a set of finite perimeter, then this energy is this weighted perimeter, but you can think as as being the integral of this function rho squared over the boundary of the set of finite perimeter, and it's plus infinity otherwise. And we also prove that whenever u is a characteristic function of a set of finite perimeter, you also have the pointwise convergence of the thresholding energies to this perimeter. And this result actually was known for a long time for the case m equals to the flat case. And there are various works around this. But the problem is that in all these proofs, the crucial ingredient is the translation invariant of the heat kernel on RK. And if you work on a curved space, you don't have this property. So this result, so we had to work to actually obtain this result, and it's new also, and it has interest in its own, I would say, and both the consistency and the gamma convergence are new, and yeah, so this corresponds to sending h to 0 in this non-local to local framework, and just to say a few words about all this, and then I will briefly talk about the second part. All this work extends to an arbitrary a number of clusters. We have to define the energies in a different way, but I mean, in terms of applications, you can take whatever number of clusters you want. Then important thing is that the MBO scheme may actually be used also to perform a semi-supervised learning, in the sense that sometimes you know already what is the value of some of the labels of your data set. And to perform semi-supervised learning with MBO scheme, you have just to change the thresholding value. Instead of taking 1/2, you take 1/2 minus square root hf, where f is a function that you construct by using the fact that you already know some of the labels. And if you do so, the energy that is being minimized will be the thresholding energy and the linear term. But the linear term in terms of gamma convergence is not really important, because I mean it will be preserved in the limit. So at the level of the theoretical analysis, the important thing is just to study this thresholding energy. And then we have different version of the Laplacian also, but it's not really important. What is important is I wanted to say is that we would like to get this convergence here. So we would like to be able to get a convergence of E when Hn and epsilon n are going to 0 jointly. And we were actually hoping to be using these two results to infer this one, but right now it seems a bit tricky. I mean, we have some because you have to have some relations between Hn and epsilon n in order for this to hold, but it seems a very hard question right now.
Yeah, so do you think it's possible to refine the result to get a quantity
No, right. I mean, we thought about it. For the moment, it seems out of reach. Yeah.
Thank you. I just wonder if you can quantify maybe that.
If you can quantify, of course. Yeah, we thought about it. No, actually, we thought about obtaining this second thing by some monotonicity property of this function this functional here in terms of h, which is known in the continuum, but we were not able to prove this monotonicity property on the graph. So for the moment, this is an open question. Sorry?
Oh, yeah. And instead of on. A question. So can you remind me again?
Sorry.
What was the assumptions on the row again? Does it need to be bounded by?
Rho is smooth, and okay, we are on a compact manifold, so okay. Smooth and it's okay. It's strictly positive, so it will be bounded away from 0 and bounded from below.
And then, so you use this standard graphical function, which has this weighting according to row, which in this is the sense in which we kind of generalized the previous work, which the unweighted. Did you look at other weightings? I mean,
Yeah. We have this we have data dependent weights also, where you reweight where you define the weights initially in this way, but then you reweight by the degrees of the, you know what I'm saying. And we also have results of the yeah. But I mean, this is just, I mean, it's just a matter of choice. You do the analysis for one Laplacian, and then yeah.
So in your argument is I minus the inverse W, please use a combined variable of the matrix. Maybe that will make us easier because
Sorry, say it again.
So here there's another graph function that is I minus the making 1/2 times W times.
This is the symmetric version. This is the only version that I'm not totally sure that we can treat. We can treat the. Yeah, I mean, I think we yes, but maybe for that one you have to change a bit the rate of convergence. But the rest one, I mean, the unnormalized Laplacian, or if you reweight the weights, this is not a problem. But the symmetric one, I would have to think about it. Yeah. So are there other questions about this? Otherwise, yeah. And then just briefly. How much time do I have actually? Okay, then even more than brief. So I want to talk about also this question about the convergence of the dynamics. And to do this, I have unfortunately to introduce a bit of material about viscosity solutions to mean curvature flow. So we are on a manifold, and for the moment, let's assume that rho is not there. So rho is the constant one. We would like to say what is the evolution. I mean, the evolution by mean curvature flow of a surface would be that the normal velocity of the surface is equal to minus the mean curvature along the evolution. Okay, and this and stated like this, you would try to check this equation using local charts and stuff. But if you assume if you take a function u, smooth function, and you assume that each level set of u moves by mean curvature, and then you try to compute all the quantities in terms of u, then you end up with this equation here. So forget about the second term, which just comes from the density. It says just that the time derivative of u is equal to this guy here, which I mean, maybe some of you would recognize. I mean, if so, g here is the value of the manifold, but if you were on an n, this would correspond to Laplacian of u minus du times this du over the norm of the gradient square, which is so this equation here is called the level set formulation of mean curvature flow, and it was introduced actually, but it was derived by Evans in his paper with Evans Sprack, where he proves where he introduced the notion of viscosity solution to mean curvature flow on Rn. And if you perform a similar computation on the manifold, you end up with this term here, which involves the metric, of course, because you are not anymore on the flat case. And okay, if you assume that you have a density, you also have a drift, which depends on the density. But I mean, for the sake of this talk, it's not really important right now. So you have this additional term. And now I say that a function u solves this system here in the viscosity sense if u is both a viscosity subsolution and a viscosity super solution of this system here. I explain in a moment what I mean by this. Just observe that the initial value here is the sign distance from the boundary of omega. So the sign distance function is just this. So you have your set omega, and you look at the distance from a point to the boundary of omega, and you take this distance with a positive side inside the set and with a negative side outside. So essentially, the sign distance is defined as so it would be the distance of x from the complement of omega minus the distance of x from omega. Okay. And yeah, in the second slide, I will explain what this is. What is a viscosity subsolution? But a fundamental theorem is that when the boundary of omega is smooth, then there exists a unique viscosity solution to this system here with initial datum given by this sign distance function. So what is a viscosity subsolution? I mean, this is the classical way in which you define it. I mean, essentially, the idea is take a smooth test function. Okay, pick a point in space-time, t0, x0. Take a smooth test function around defined in the neighborhood of this point, which is tangent to your function u from above. So you have your function u maybe, which is like this, and you take a test function which touches the graph from above. And essentially, what you want is that this test function here should satisfy the equation that I want to define the mixed solution for with an inequality. So as you see here, this is exactly the same equation that we had before for the test function, just which comes just with an inequality. And this should happen if the gradient of phi, of course, is not 0. at this point here. If it's 0, then you ask that there exists a covector in the cotangent space of the manifold, which satisfies this inequality here. But I mean, just focus on this case, which is the really important one. And okay, and you say that U is a subsolution if this holds for every test function and for every point. And you say that U is a super solution if this comes with a reverse inequality. Okay, and then a solution is both a subsolution and a super solution. Okay, so this is all I wanted to say about the definition of viscosity solutions. So to answer to the third question, we put ourselves in this setting here. So we pick a smooth open set on the manifold, and for each graph that we have, we intersect omega with the graph producing this omega n. Okay, and then we pick a sequence of step sizes converging to 0. And then for each graph n, I can consider the dynamic of the MBO scheme for the fixed graph. So I start the MBO scheme on the nth graph with step size hn and with initial value omega n, and I produce infinitely many characteristic functions chi L gn, where L ranges over all the natural numbers. So I just consider the evolution for infinitely many times. And then, okay, instead of working with a characteristic function, I want to work with a -1 valued function. So I just redefine functions here, u, h, and gn by this formula. So this converts the set where chi is equal to -1 and the set of where chi is equal to 1 to 1. And then you define these two functions here. So this is the upper semi-continuous envelope of all these functions that I have defined. And this is the lower semi-continuous envelope. So the upper semi-continuous envelope is a sup. You take a sup over what? Over sequences of points, Tn, Xn, where Tn converges to T, and Xn converges to X. And Xn has also the property that the Xn lies on the nth graph. And then you take the sup of the lim sups over all these sequences. Okay, so that's why the upper semi-continuous envelope. And in the same way, you define the lower semi-continuous envelope by substituting sup with inf and lim sup with lim inf. Then we have the following result. So we consider U the unique viscosity solution with initial value given by the sign distance function, which we know to exist by the theorem of Ilmane. And then we consider these two sets here. For every time t, this omega t is the set of points where u is greater than 0. So this encodes the interior part of my evolution, because this was true for the initial set. And then gamma t is the set of points where u vanishes. This would encode my boundary. And the result that we have about the convergence of the dynamics is the following. So you take epsilon n another time converging to 0 with a given rate. Now we also have assumptions depending on the geometry of the manifold, which bound the rate of epsilon n from above, but I mean, it's not important right now. And then you also assume that we have, this is really important, the following rate of convergence of Hn with respect to epsilon n. So if this is satisfied, we have convergence of the dynamics of the MBO to mean convergence of flow in the following sense. So the functions that I have defined before, essentially they are able to detect the interior part and the exterior part of the evolution, because U star, U lower star is one in the interior part of my evolution, and the upper semi-continuous part of U is -1 on the exterior part of the evolution. So this is really the classical way in which you prove convergence of MBO to the notion of viscosity solution for mean convergence of flow. And pay attention that here we identify, I mean, we get this rate, hn to the 3/2 must be much larger than epsilon n. Now, this is not optimal. The critical value should be hn over epsilon n much larger than 1. But currently, we are not able to do this. I mean, already for this, it's quite some technical work. So there is for sure room for improvement, but we have no idea on how to get a better rate for the moment. Just a couple of remarks about this. So this the proof of our proof is inspired by the same results where they prove convergence of MBO to mean coverage of flow in the continuum, and these are results by Balser, Georgelin, and actually also by Mistias and Yip. Actually, this is already working on a discrete grid, so they are working actually on the torus. So this is already working on a graph, but they are not working on regular grids. And of course, for regular grids, you already have an expression for the heat kernel, so it's easier. And actually, in that work, they obtained the right rate of epsilon and hn, but this is restricted just to regular grids. Then I must say that the proof relies heavily on the convergence of the spectra of the graph Laplacians to the spectrum of the limiting operator. And these are, works by Calder, Garcia Trillos, and Levitschka. And there are some assumptions that we have to impose on the manifold. These are technical, but I want to say that this, so it does not hold for every manifold, like not for every compact manifold as the previous results. And to conclude, let me say that when we are in the continuum and you work just on the MBO, on the flat case RK, so you work with the classical MBO scheme, the convergence of the dynamics in the viscosity sense was already proved by Evans, Balser, Georgelin, and Ishii, Pires, and Sugarinidis. And only much later, in 2016, there was a proof of the convergence using this minimizing movement interpretation, and in particular towards a notion of solution stated in terms of sets of finite perimeter. But for these works, one of the crucial ingredients is the gamma convergence of the thresholding energy. So if you want to prove this second item, also in this graph setting, the missing ingredient, the main missing ingredient is still this joint gamma limit that I was talking in the first part. So if you don't understand the gamma limit jointly as hn and epsilon go to 0, there is no hope that you can prove the convergence of the scheme in these sets of finite perimeter framework. So it would be really interesting to prove this result, but for the moment we don't know how to do this. And yeah, I think I can stop here. I just want to say that for the first part, there is already a paper on the archive from December, I think. And the second part, this convergence of the dynamics, I'm sorry, we were not able to write it down for this talk, but it will be soon, probably next month on the archive. Okay, so thank you for your attention.
Very much for the wonderful talk. Is there any questions?
I wanted to ask you a little bit about the motivation that you have when you're starting this on graph.
Mm-hmm.
What the certain graph from clusters which are highly correlated, and you get that. And you use the heat flow to do it, and it kills all the stuff which is not correlated. But doesn't it do something to these highly correlated clusters as well?
I mean,
It makes smooth.
yeah, this makes smooth, but then you are able to cluster them because yeah. I mean, if they are highly correlated, okay. I mean, if they are highly correlated, there is always the chance that you lose the information. I mean, I cannot tell you what's the correlation, the correlation that you have to have in order for the scheme to be able to detect them. This is something which I mean, quantifying the correlation is difficult. So I mean, in terms of applications, I don't know if you can really say, okay, the graphs are, the clusters are, okay, the data points are so correlated, so and so, and then I will be able to detect those clusters. This is not something that we can do, and also we didn't do this, because I mean, here we are looking really at what happens in the limit, whereas your question is more in terms of I fix n, I have this correlation, will I be able to detect the clusters? So yeah.
And you know, identifying the clusters, I mean, if they were, you know, solutions of the Laplacian, if you go to zero, I mean, they're taken with solutions, then maybe you can figure out what they are.
Yeah.
But that's not necessarily the case.
No. And also, then the scheme is never used like this. So the scheme is never used in this way, because you look at the minimizers of the really just the threshold in energies, the minimizers have just the zero function or the constant one. So of course, this is not really informative. That's why I also included this slide on the semi-supervised MBO, because when you put also some information on the labelings, then the minimizers are non-trivial, and that's how the scheme is really used. But I mean, at the level of analysis, you're just interested in the asymptotic behavior of this energy. But if you want to apply things, then you always put also a forcing term. So you either you put a constraint on the mass, which is the thing which actually is done when in this simulation here. Here actually we are not really using just this scheme. You use this scheme and the fact that the two clusters have to have the same mass. This is the constraint. Otherwise, you use this labeling function to I mean, maybe you know some labels and you want to use this information plus the geometry of the data set to infer the. But otherwise, if you run infinitely many times MBO just like this, you will always converge either to the constant one or to the constant one, zero.
Yeah, I have maybe some other questions just to ask. Is like the more considering the data is contaminated by noise, how to affect this algorithm and study the much stable unit?
You mean when the data points are close to a manifold but not on the manifold?
Yeah.
Actually, this is a very good question. We wanted actually to start doing this too. We didn't try. Probably the convergence will still be true, but of course you will have to make some assumptions on the noise. Not every noise will work. But of course, this is a very good question, and actually, it's more interesting probably because in the application you don't really have data on a manifold, but you will be close to a manifold. So actually, this is something we wanted to study.
Any other questions? If not, let's thank Jona.